Howdy. Oh my goodness, I didn't get like a
Howdy.
Howdy. Yes. That's how people greet in like Texas.
Oh, I know.
You know that.
I studied in Florida, and it was already the same.
Oh, howdy as well in Florida. Okay, cool. They copied us.
That I don't know.
So it's my great pleasure to have Dan as well as Hugues from the CAMECA today to teach us about atom probe. As many of you know already, we're planning to purchase an atom probe through an SF. So today is a really good opportunity to learn more about this technique. So without further ado, let's welcome Hugues to teach us about APT.
All right. Good morning, everyone. Nice come flavor. Good morning, everyone. My name is Hugues Francios-Saint-Cyr. Everybody calls me H, because it's easier. I've been with CAMECA for about 14, 15 years. I've worked on many different product lines, but right now I'm focusing on atom probe. And basically, I wanted to share with you what this technique was able to deliver in terms of research, and how it could maybe help you in succeeding in your field. So, in particular today, I'd like to talk a little bit more about the EIKOS-UV, which is the latest product line that we have launched. It was in August this year, and we hope that to be able to get this instrument to move forward with your research. So, what I plan to do today is I plan to introduce you to the technique. Not many people know about this technique, maybe more and more, but not enough so that I can pass on the introduction. Then I'll go specifically about the EIKOS-UV and give you the specificity of this product line. And then I'll move with some applications that we have already developed with the atom probe. So today we'll talk about nickel-based superalloys, additive manufacturing, LED devices, a bit of non-conductive materials such as the fiber optics or ceramics, and grain boundary analysis. And if we have time, maybe lithium-ion batteries. And then we can open the floor for discussion. So, quickly, 2 or 3 slides about CAMECA. CAMECA is part of AMETEK. AMETEK is a huge company with a lot of business units. You probably are aware of EIVAS or Spectral or material characterization system. So this is still part of AMETEK, the material analysis division. So CAMECA is part of it, and our bread and butter is secondary ion mass spectrometry, EPMA, macro probe analyzer, and atom probe. So the atom probe are exclusively built and designed in the US. So quickly, we have EPMA systems, we have the secondary ion mass spectrometers, and they are specific to different application fields as well. And we do have the atom probe. So we're going to focus today really on the atom probe product lines. So where would the atom probe fit in terms of the material characterization landscape? I'm quite sure that if you are in material science, you are aware of a lot of techniques that you need to characterize your materials. I mean, it's unlikely that if you have to tackle on a specific study that you will focus on one technique to give you all the answers. You have to correlate the answers from different techniques to get the full 360 view on your study. So if you look at the landscape of the material characterization techniques, each technique has something in particular to bring to the table. If you are analyzing something with the secondary ion mass spectrometry, the SINS, for example, you can get up to part per trillion detection. So this is really basically the ultimate technique for that range to detect. However, in terms of lateral resolution, it's a little bit short, falling short. When you have TEM, for example, the TEM you can have atomic resolution, but it's basically a 2D image that you're gonna get, unless you have maybe the rotation that you can put on it. But where atom probe would come in place is it will fill this gap here, where it's actually an imaging technique. You have atom by atom evaporation and detection, and you have the resolution that is also in the sub-nanometer region, and it's in 3 dimensions. Okay, so that's what makes it really, really powerful. To give you a quick example, if you have LED with quantum wells here, if you have a high angular dark field image, you could think that, okay, these layers here seems to be great, and there's no defect there. Well, if you transpose that to the atom probe, you will also find in the 3D volume all these layers. But then if you go further and take slices, very thin slices at different locations of the volume, you see that these layers are not actually uniform. Okay, the TEM wouldn't be able to give you this information. The atom probe can. So why am I here to talk about atom probe? It's just because if you look at the curriculum in colleges or universities, you have a class for SEM, you have a class for TEM, you have a class for FIB, you have a class for SIMS. I'm still waiting for a class for atom probe. Okay. First of all, you need to have an atom probe, and then even if you have an atom probe, it's difficult to find a slot for you to get a class for atom probe. So this is my job. So not only is it important that I give you some information about the atom probe, but if I put that in perspective in terms of the research, up to about 2003, the number of publications per year was actually plateauing at about 200 publications a year. After we have introduced the local reactor atom probe, the commercially available atom probe, now you have an explosion of publications that would occur every year. And this explosion, this adoption really of the technique, came after we have introduced the UV laser in our systems. Okay, so you have the voltage pulse mode only, you have the voltage and the green laser, and you have the voltage and the UV laser. When you have the UV laser, you really enable a broad range of applications. Okay, so we have the Liftout X system, and we do have the EIKOS-UV system. I believe this is the one that is of most interest to you. And we think about the different applications. We still have about half of the applications that are still metal, but we have a split with other fields right now, enabled by the UV laser. So let's give a little description of the atom, how it works. Basically, it started with in 1956 here, the first way to get the atomic resolution that was by Europe, and you could see actually the evaporation of terraces. Okay, so that was wonderful at that time, but it was slow, and it was also it wasn't an atom probe; it was a field ion microscopy. So if you do have now instead the atom probe, you will have a specimen that is about 50 to 100 nanometer at the apex, okay, in a needle shape, and I'll explain a little bit later how we get to that needle shape. It's in a cryogenic environment. It's in ultra high vacuum environment, and then you have the electric field that is applied, or you have a high voltage that is applied. But with this high voltage, you should not have any evaporation. However, if you add a little pulse, whether it's a field pulsing or thermal pulsing, if you have a voltage pulse or a laser pulse, you could trigger or give a chance for the ions to take off from the tip and go to the detector, the position sensitive detector. So with the position sensitive detector, you basically have the X and Y position, but you don't have the Z position. So it works as a time of flight. technique. So basically, the ions are flying from the tip to the detector, and the time it takes for the ions to arrive on the detector will actually give them their chemical identity. Okay? And this works because we are balancing the potential energy with the kinetic energy, and by doing so, the chemical identity here is given by the time of flight squared. Okay? So you have a number of peaks that are first in time of flight, and then they are in mass over charge ratio, and they relate to specific elements. And then you can actually then get the reconstruction in 3 dimensions based on the sequence of evaporation. You get the Z dimension. Okay, so you can see here that in 3 dimensions, if you think that these layers were actually without defect, if you get the full volume, you could see that it's not the case. You have the defect here. Okay, so how do we get to this needle shape that I discussed? Well, you have the general Liftout method, where you deposit, for example, a platinum strip on the top of your sample to protect it from the gallium, for example, and also to mark the surface that you are interested in. Then you actually dig like a U shape around this lamella, and then you approach the micromanipulator to the end that's actually free. You glue it, and then you cut the lamella free. You lift it out and put it on, for example, here, micropost. And then you cut it and you put it on many microposts. So you end up with what we call the Toblerone shape here. Okay. So once this is done, you can proceed to the annular milling in the field until you get really the shape that is desirable for atom force, like a needle shape, 50 to 100 nanometer at the apex. And you need to make sure that you apply a low KV finish at the end to remove any contamination that you have put with the gallium. Okay. Now, there's a traditional technique, which is the electropolishing. Okay, so if you don't have a FIB, or if you work with samples that do not require site specificity or do not have an issue with electropolishing, then you can actually get to a fast preparation of your tip by having a matchstick and then using an electrolyte, a closed circuit with voltage and current. And then for each matchstick, you can create 2 tips that are very sharp as here. Okay? So you can use that as well as a technique. So we do have several technical notes that we could provide you if you are interested in preparing some specimen. It doesn't matter which FIB manufacturer you are using. This is a guide, okay, so you can adapt it to your system. And you have it for the LIP system, and you also have it for the EIKOS. Okay, so you have different approaches that you can use. Now, let's talk about maybe the EIKOS-UV. Since the last time we came here, we focused on the LIP and we could focus on the EIKOS previous generation, which has a green system. The problem with the green system is that there are lots of applications that you cannot do. It's limiting the range of applications that you can use. So now we have broadened this range by actually adapting a UV laser to the EIKOS system. Okay, so we launched this instrument 6 weeks ago, and it's basically now considered as the workhorse of atom probe. It's reliable. It's giving you really the result that you should expect with the reflection system that we have, and I will explain to you what that means, reflection system. But basically, it actually is the result of our thought process from the time that we have worked on developing the technique. So we launched the first system in 2003, but before that, we actually took some brain power way before that to be able to get to that point. So we have about 30 years of experience here in Atom Probe. And what's really interesting is that with the UV system that we have fitted here, we can reach out to lots of different fields in material science. Okay? So whether it's metallurgy, whether it's oxide, semiconductors, I mean, not semiconductors, but I would say functional devices. Okay, so LEDs and so on. So basically, we still do have the single atom detection with the EIKOS system. It's still based on the time of flight. So we still do have equal sensitivity to all elements. We start from the hydrogen up to the, I don't know, uranium if you wanted to. And it's still in the atomic level if you wish to actually reach that level for your material. Okay? So you can use for metals, coating films, ceramics. It's really much broader than before. The other point that is important to make is that when you get an EIKOS-UV, not only is it easier to use than a regular LEAP system, but it's also much cheaper on the long run. Okay? And that's important, especially for universities and colleges. It's important to be able to have this room to maneuver. Okay? So, I said I would come back to the reflection system. The reflection system is what we call basically, it's an energy compensating system. So when you do have some ions leaving the tip at different location or different timing of the voltage pulse, then what happens is that they could not arrive at the right time on the detector. So with the reflection system, we have a way to compensate for that deficit in energy, so that it actually reaches time of flight, and therefore the mass spectrum will give you very sharp peaks, and you can do a better quantification, more accurate quantification. So if you don't have a reflection, for example, if you are subject to this energy deficit, you see that these peaks here are really broad, and it's difficult between peak to peak to have peak to background. Okay, so it's difficult to do a good job in terms of quantification. If you have an energy compensating system, you see you have a peak and it goes down to background, and a peak to background, and a peak to background. Here, it's not that much of a problem for tungsten because those are just the tungsten peaks. But imagine that you have two different elements or two different materials next to each other, then you have an issue doing the proper quantification. Okay? So, and of course, in UV laser mode, you will have actually peak shapes that are much sharper than in the gray. Another advantage that we have with the EIKOS compared to the system that is much more expensive, for example, is the integrated counter electrode. Okay? I don't know if you recall, Kelvin, when you were in Sydney and you had the LEAP systems, and you have local electrode, and this local electrode is basically you had to be very, very careful with them because number one, they were very, very expensive, and if you had some fractures, then you could actually not be able to use this local electrode for long. In this case, we do have integrated counter electrodes that are much cheaper than the cost of local electrode that you have in the LEAP system. And also, you align the tip with the counter electrode outside of the system. Okay, and that's a big advantage because you don't have to deal with inside vacuum issue if you have to align it inside. Okay, so you align it outside, so it's pre-aligned so that it's ready to get into the system. So we provide, of course, the hardware to be able to do this alignment. We have a crimping station and an alignment station, and it's fairly straightforward, okay, to learn. To be able to actually get this puck and this sample secured into this counter electrode. So I hope it's gonna play here. Yep. So basically, this is the station with all the tools that you need that are already integrated, and then we can show here the integrated counter electrode that you secure. You place the specimen, then on the top of that you place the local ILE control, the local electrode here. Then you position in XY, and then you position in Z. Okay. Once this is done, then you secure completely your puck here, and this is ready to go into the atom probe. Okay. So again, it's fairly simple as a process here. So what is even more remarkable, and again, I'm going to reach out to you, Kelvin, by saying if you have a leap system and you need to align it in laser mode, sometimes it can take long. Sometimes it's easy. Sometimes it's going to take longer, and it depends also on the material. Right? In this case, we made it really easy because the sample is not going to move. It's already fixed with respect to the integrated local electrode here, and we also have it automatized. So that means that if I'm gonna play that now. You see, it started here already where you have some automation, transfer assist. The automation, which means that if you want to move a sample from the buffer chamber to the analytical chamber, you click on a button and it positions exactly the puck before the entrance and opens the gate valve. All you have to do is use the horizontal rod to put it in, and then when you click on laser, it's gonna go and do the laser search on its own. Okay, so it does the laser search on its own. This is just a message saying that we haven't waited 15 minutes before we started the experiment. But basically, right now, it's less than a minute. It's ready to go. Okay, so this is much easier than what you would have to do, for example, with the leap system. We still do have so we have this automated alignment, and we also do have a large dynamic range. That means 6 orders of magnitude in the laser pulse energy that you can use, because every material is different. So every material will actually require a different amount of laser pulse energy for the evaporation of the ions. Okay. And basically, we do have the system that is really easy to use. That's really the key point here with the EIKOS system. So this is just an image of the laser on the tip once it's aligned. The good news also is that the EIKOS-UV is surfing on the wave of the new developed Atom Probe Suite software. And this Atom Probe Suite software encompasses the database for the generation of samples, but also for the acquisition of the runs, as well as the analysis, the post-processing of the data. So with this AP Suite 6, we do have the management of the systems, the management of the samples, and we also do have live calibration. And you can also, if you are a bit more advanced in Atom Probe, write your own code and plug it into the system. So this is really really good thing to do. This is just 2 examples that I wanted to show because they are difficult examples. We have buried oxide. There's an oxide here, and you see that has been analyzed with EIKOS-UV, no problem. And you have a mineral sample that has a lot of different elements, but we also have no issue going to 400 nanometers here in depth, for example. Okay. So now it's time to maybe move toward applications that are really fully developed here. So if we look at nickel-based superalloy, I start with this sample that has actually been prepared by FIB system, FIB protocol, and you see that the mass spectrum is very populated. Okay, you have a lot of different elements or different mass to charge state ratio here. And what I wanted to focus on here is the fact that whether you are at the low end